Welcome to this AP Calculus video on related rates. Let's get started. So first I have a warm-up problem for us to consider. Let's think of a sphere of radius 10 centimeters. If the radius changes by 0.1 centimeters, use differentials to estimate how much the volume will change. Well, just learned how to do this recently. So we're going to take the formula for volume of a sphere, volume equals 4/3 pi r to the third power. And we're going to take the derivative with respect to radius. So we could call it dv dr, or we could move the dr to the other side and say that dv is equal to 4 pi r squared dr. This is the derivative times a small change in r. So if I multiply the derivative times a small change in r, I'll get a small change in v. And this is a way we're going to estimate the change in volume. Now we'll plug in 10 for the radius, plug in 0.1 for the change in r. And by doing this calculation, 4 times pi times 100 times 0.1, we wind up with 40 pi cubic centimeters. That is our estimate for how much the volume would change. Now, if we actually check this, the volume actually changes by an amount slightly larger than 40 pi. This is the volume at 10.1 minus the volume at 10. The actual change is about 126.925, and 40 pi is only 125.664. So we do get a good estimate, but it is not perfect. Next, I want to recall something we learned a little while back called implicit derivatives. So we had problems like this: find dy dx when x equals 3 and y equals 5. And then we were given a formula which involved a mixture of x's and y's, where we understood that x was a variable and y was actually an implied function. So when we took the derivative, we just went term by term, and the derivative was 6x minus, for this we had to do a product rule, negative 12x times y minus 6x squared times dy dx, and then plus the derivative of this term, 12y squared dy dx. And every time we did a derivative of a term that involved y, we had to do the chain rule. So we had to treat it as though it was a function of x. So the derivative of y was not just 1, the derivative was dy dx. To complete this problem, I just simply plug in and solve for dy dx. In this case, it comes out to 162 over 246. Now, why did we treat the variable y so much differently than the variable x? Well, the reason was because we understood that y was representing a function, an implied function, but we understood x to just be a variable. But what if we viewed this problem in a slightly different way? Let's say that we took both variables x and y, and instead of saying that one was a variable and the other was a function of that variable, what if we considered each of them to be a function of some third variable? So let's suppose we said that y is an implied function, but y is some function of t. And what if we said that x was also an implied function, but x was also some function of a third variable, t? Now when I do the derivative of 3x squared, I'll need to do the chain rule. I'll say that its derivative is 6x times the derivative of the function x, which is dx dt. And again, I'll have to do a product rule here. The derivative of minus 6x squared will be minus 12x times the derivative of x with respect to t. Multiply that times the function y. And then for the other part of the product rule, negative 6x squared times the derivative of y, but we'll write the derivative of y with respect to t. And then finally, the derivative of 4y cubed. That's going to be 12y squared times the derivative of that implied function. So times dy dt. The 16 doesn't have an x or a y, so its derivative is just 0. So we've just done an implicit derivative again, but this time treating x as an implied function and y as an implied function. We're saying that both of these are quantities that change with respect to this third variable, t. Let's see how we might use this concept in a problem. Suppose the radius of our sphere is changing at an instantaneous rate of 0.1 centimeters per second. So unlike the other problem that we started with, now we're given a rate of change, not an amount of change. This could be possible if you're maybe blowing up a soap bubble or a balloon or something. We'll start with the formula V equals 4/3 pi r cubed, the formula for volume of a sphere. And we're going to take the derivative, but this time we're going to treat r as an implied function of t. We're also going to treat v as an implied function of t because both of these are quantities that change as time changes. So we'll write the derivative of v, dv dt, equals, and then the derivative of 4/3 pi r cubed is 4 pi r squared times dr dt. Using the same initial radius of 10 and the given instantaneous rate of change of radius, 0.1, we can do this calculation. 4 times pi times 10 squared times 0.1. And this time it's telling us the rate of change of v. So dv dt is equal to 40 pi, and our units are cubic centimeters per second. Now, the interesting thing here is that this is not an approximation. dv dt is exactly 40 pi cubic centimeters per second. This is an example of what we call a related rates problem. Basically, we've related two derivatives. Here are some guidelines for doing related rates problems. Step one is to draw a picture or a sketch. Most of the problems that you deal with are going to involve some kind of quantities in a real life situation, and it's helpful to draw a picture and label as many values as you can. Step two is to write down the known information. Some of these would be, for instance, a radius that's given, or a height that's given, or any other kind of dimension that's given, or an angle. Also, along with that known information, there should be some rates that are given. And finally, write down what you are looking for. Usually the thing that you're looking for is also going to be a rate. And when you're given a rate or when you are looking for a rate, it usually helps to name them in a way that reminds you that it's a derivative. For instance, a rate of change of volume would be dv dt, rate of change of radius, dr dt, rate of change for an angle, d theta dt, rate of change of height, dh dt. Step four is to write an equation that relates the variables. That equation is not going to have any derivatives in it. It's just going to be an equation, for instance, relating volume and radius and height. Don't expect to see any of those derivatives in that original equation. Step five is to differentiate both sides with respect to t. Here's where those derivatives are going to be introduced: dv dt, dr dt, dh dt, d theta dt. Finally, evaluate. That is, take all the given numbers that you're given and solve for the one thing that is unknown. Now, it's very important that you do not input values until after you differentiate. If you start inputting values before you differentiate, you are most likely going to come up with the wrong relationship between the rates. Here's a second example. Water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? So I'm going to write down the things that I'm given. It says the water is draining 3 liters per second. So I'll write that as a rate. The volume is changing. It's losing 3 liters. That is a negative 3 liters per second. I could also write liters as 1,000 cubic centimeters. So we could say the volume is changing by negative 3,000 cubic centimeters per second. So these are ways of writing one of the known quantities. That known quantity is a rate. The question asks, how fast is the surface dropping? So the surface of the water in this tank, we're going to call that the height of the water. So how fast is it dropping? That's a rate. What we're looking for is dH/dt. That is our unknown, dH/dt. So I need some kind of a formula relating to cylinders that has volume and height. That formula would be the volume formula for a cylinder. Volume is equal to pi r squared times height. Now it's time to differentiate. We're going to differentiate volume, knowing that volume changes over time. We're going to differentiate height, knowing that height changes over time. However, the radius of this tank does not change over time. So the radius is actually a constant. It is not a variable. It's going to be wrapped up with this constant pi. So the constant pi r squared times h, the derivative is going to be pi r squared times dH/dt. So dV dt is equal to pi r squared times dH/dt. Now we're going to evaluate this. Replace dV dt with negative 3,000 cubic centimeters per second and divide by pi r squared so that dH/dt is by itself. We find that dH/dt is equal to negative 3,000 cubic centimeters per second divided by pi r squared. So the rate at which the height drops is actually going to be dependent on the radius of the cylinder. If this cylinder is very thin, that height is going to drop quickly. If this radius is very large, the height is going to drop more slowly. Here's another example to consider, the hot air balloon problem. Suppose a hot air balloon is rising up into the air, and we are standing right here 500 feet away from the launch point of the hot air balloon. Now, as that hot air balloon rises, we'll have to tilt our heads back farther and farther to get a view of the balloon. We'll tilt our heads at some angle, let's call it theta. Suppose we're given that theta is pi over 4. That's the same as 45 degrees, so our current angle that we're tilting our neck at is pi over 4. Suppose we are also given that d theta dt equals 0.14 radians per minute. That is, that's the rate of change of this angle. We are increasing our angle that our neck has to be tilted at to follow the balloon as it goes up, and it's happening at 0.14 radians per minute. What I want to try to find is how fast the balloon is rising. That is, what is the change in height? Well, I gave the change in theta a name that reminds me that it's a derivative. Let's give the change in height a name that reminds me that it's a derivative. We're going to try to find dH/dt. What I need now is a formula that relates theta and h. Well, this is a right triangle. We can actually use right triangle trig in this problem and say that the tangent of theta is opposite over adjacent, or tangent of theta equals h over 500. Our next step is to differentiate both sides. Remember, theta is something that changes over time, so we consider that to be an implied function of time. Height is something that changes over time, so we consider h to be an implied function of time. The derivative of tangent theta will be secant squared theta d theta dt. The derivative of h over 500 is going to be 1 over 500 dH/dt. Now it's time to plug in our given values and solve for the unknown. We were given that theta equals pi over 4. We're given that d theta dt equals 0.14. Plugging those values in, we need to solve for dH/dt. All I need to know is what the secant of pi over 4 is. Well, I know cosine of pi over 4 is root 2 over 2, so secant of pi over 4 must be the reciprocal 2 over root 2. Plugging that in place of secant pi over 4, now we have 4 over 2 times 0.14 times 500. And that works out to 140 feet per minute. That's how fast that balloon is rising right at that instant. As our last example, we're going to do what I call the truck problem. Suppose two trucks leave from the same point, one traveling east at 40 miles per hour, another traveling north at 30 miles per hour. How fast is the distance between the trucks changing 6 minutes later or 6 minutes after they leave? First thing I'm going to do is try to sketch a picture of this. I've got truck A traveling east, I have truck B traveling north, and each of them has its own rate of travel. Remember that distance is equal to rate times time. So if I take the rate of 40 miles per hour times 6 minutes or 1/10 of an hour, that means that truck A has traveled 4 miles. So the distance here is 4. If I take 30 miles per hour times 6 minutes or 1/10 of an hour, I get 3 miles that truck B has driven. So the distance there is 3. The distance from B to A is actually very easy to find. This is a right triangle, therefore Pythagorean theorem applies. We have legs of 3 and 4, and we're trying to find the distance here. 3 squared plus 4 squared gives us 25, and so the length Z is 5. It's a 3, 4, 5 triangle. But remember, the question was not what is the distance between the trucks? The question was how fast is that distance changing? We can call the thing that we're looking for dz dt. We can call the rates that we're already given dx dt and dy dt. So we now have all these different values, and we're going to try to find the one that's missing, the dz dt. Well, I'm going to start with a formula that relates x, y, and z. Well, that's Pythagorean theorem. X squared plus y squared equals z squared. I'm going to differentiate, and any value that changes over time, I have to consider it to be an implied function of t. So the derivative of x squared is going to be 2x dx dt. The derivative of y squared is 2y dy dt. The derivative of z squared is 2z dz dt. As I look at all the values I'm given on the right, I see places where I can plug all those values in. Divide both sides by 2 first, but we still have 4 times 40 plus 3 times 30 is going to equal 5 times our unknown rate of change. Solving for dz dt, we get that dz dt equals 50. So the distance between the trucks is changing at a rate of 50 miles per hour. One last quick tip before you start trying these problems yourself. When you're given a rate of change, pay attention to whether that rate of change is an increase or a decrease. For increases, we want to make our rate of change positive, but for decreases, we want to make our rate of change negative. That can have a very big influence on the outcome of your problem. Now it's time for you to try some of these problems. Try the assignment on My Math Lab. This assignment is actually broken into 2 parts. So go ahead and give them a try, and we'll see you next time.